Tonight, we're going to explore something that feels obvious until you actually try to pin it down. Space and time. You think of them as two completely different things. Space is the distance between you and the wall across the room. Time is the ticking of the clock on that wall. One feels like a place, the other feels like a flow. But here's what almost nobody realizes until they dig into the physics. Space and time are not two separate things that happen to coexist. They are a single object. They're stitched together so completely that cutting one away destroys the other. And by the end of tonight, you're going to understand why the universe doesn't actually contain space and time as two ingredients. It contains one ingredient called space-time. And that single fact reshapes everything from falling apples to black holes to the birth of the cosmos itself. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with the way you already think about space and time, because that's the picture we need to take apart first. In everyday life, space feels like a stage. It's a fixed backdrop of up, down, left, right, forward, and backward. It sits there quietly while things move around inside it. Time feels like something completely different. It's a river flowing steadily in one direction. It carries events from the past into the future, the same for everyone, everywhere. You wake up, you eat breakfast, you go to work, and through all of it, you assume that a clock in your kitchen and a clock on the other side of the planet are ticking at exactly the same rate. You assume that if two things happen at the same moment for you, they happened at the same moment for everyone else too. This picture isn't stupid. It matches everything you can perceive with your own senses. It's also, as it turns out, completely wrong. Not wrong in a small, technical way. Wrong in a way that took the most brilliant minds in physics centuries to even notice. And once they noticed, it forced a total rebuilding of how reality works. This picture of a fixed stage and a universal clock has a name. It's called Newtonian space and time, after Isaac Newton. He formalized it in the 1680s. Newton described space as an absolute container, existing on its own, unaffected by whatever objects happen to be sitting inside it. Empty space, in Newton's view, was still something. It had a definite geometry, distances that meant the same thing to every observer. It would go on existing exactly the same way, even if every star and planet in the universe vanished. Time, in Newton's system, was equally absolute. It was a single, universal clock ticking away in the background of existence. It was the same for a person standing still and a person riding in the fastest carriage imaginable. It was the same on Earth and the same near a distant star. Newton even wrote that time flows equably, without relation to anything external. This wasn't just philosophy. It was the mathematical foundation underneath his laws of motion and his law of gravity. Newton himself offered a famous thought experiment defending the idea that space had to be absolute. It's known as Newton's bucket. Imagine a bucket of water hanging from a rope. It gets twisted up tightly and then released, so the bucket begins spinning. At first, the bucket spins, but the water inside stays still. Its surface stays flat, because the water hasn't started moving with the bucket yet. Gradually, friction drags the water into spinning along with the bucket. As it does, the water's surface becomes concave, climbing up the sides of the bucket. It's a familiar effect anyone who has stirred a drink has seen. Newton asked a deceptively simple question. What is the water rotating relative to? It can't be rotating relative to the bucket. At the moment the water's surface is flattest, water and bucket are moving at the same speed relative to each other. And at the moment the surface curves most, they're again moving together, spinning as one. Newton argued the water must be rotating relative to space itself. He called this absolute space, an independently existing backdrop against which true rotation and true motion could be measured. This argument stood largely unchallenged for over 2 centuries. It's part of why physicists were so slow to give up the idea of an absolute, independently existing space. It took Einstein's general relativity to finally offer a different answer. In that answer, the water's rotation is measured not against empty, absolute space. It's measured against the local structure of space-time itself, shaped by all the mass and energy in the surrounding universe. It's a subtle but crucial difference. It removes the need for space to be a fixed, independent stage at all. And for over 200 years, it worked. It worked so well that it put people on the moon. It predicted the orbits of planets with stunning accuracy. It explained falling objects, cannonballs, tides, and comets. There was no reason to suspect that space and time were anything other than the fixed, separate backdrop Newton described. Until physicists started paying very close attention to light. Light is where the whole Newtonian picture began to crack. In the 1860s, James Clerk Maxwell worked out a set of equations describing electricity and magnetism. Buried inside those equations was a strange prediction. Light was an electromagnetic wave, and it traveled at a fixed speed, about 300,000 kilometers per second. That number fell straight out of the mathematics. It had no reference to who was measuring it or how fast they were moving. But under Newton's picture of the universe, speed is always relative to something. If you're on a train moving forward and you throw a ball forward, someone standing on the platform sees the ball moving faster than someone sitting still on the train would measure. Velocities add together. That's common sense, and it had never failed before. So physicists in the late 1800s assumed light had to work the same way. They imagined a substance filling all of space, called the luminiferous ether. It was a medium that light waves rippled through, the same way sound ripples through air. If the ether existed, the Earth should be moving through this ether like a ship moving through water. After all, Earth orbits the Sun at about 30 kilometers per second. Light traveling in the same direction as Earth's motion through the ether should measure differently than light traveling against it. That's the same way sound from a moving source shifts depending on direction. In 1887, 2 American physicists built an extraordinarily precise instrument to detect this difference. Their names were Albert Michelson and Edward Morley. They split a beam of light in 2, sent the halves in perpendicular directions, then bounced them off mirrors and recombined them, looking for the tiniest shift caused by Earth's movement through the supposed ether. Finding it seemed like it should be easy. They found nothing. There was no shift at all, no matter which direction they pointed the device, no matter what time of year they ran the experiment. Light moved at exactly the same speed in every direction, regardless of Earth's motion through space. This result confused physicists for almost 2 decades. Some tried to patch Newton's picture with increasingly awkward fixes. Objects were said to contract slightly as they moved through the ether. Clocks were said to run slightly differently, for no clear reason. The patches worked mathematically, but nobody could explain why nature would behave that way. It took a young patent clerk in Switzerland to realize the patches were pointing at something much deeper. Before Einstein arrived at the full answer, two other physicists had already stumbled onto pieces of it, without realizing what those pieces actually meant. Dutch physicist Hendrik Lorentz worked out a set of mathematical equations, now called the Lorentz transformations. They described exactly how measurements of space and time would need to shift between observers moving at different speeds in order to keep the speed of light constant. Irish physicist George Fitzgerald proposed something similar. He suggested that objects moving through the hypothetical ether might physically contract along their direction of motion. That would explain why the Michelson-Morley experiment found nothing. Both men treated this contraction as a real, physical squeezing caused by the ether pushing against moving matter. It was a mechanical explanation for a mechanical universe. The mathematics was correct. The interpretation was not. Lorentz and Fitzgerald were patching a broken picture. They were adding a strange new rule to a universe that still had absolute space and absolute time sitting underneath it. Einstein looked at the same equations and asked a completely different question. What if there is no ether? What if space and time themselves are the things doing the shifting, not some invisible medium pushing on solid objects? That reframing is the entire revolution. Lorentz had the correct formulas years before Einstein published his paper. Yet Lorentz never stopped believing in an underlying, absolute ether hiding beneath it all. Einstein removed the scaffolding entirely and kept only the building. He showed that the Lorentz transformations weren't a strange side effect of matter interacting with a hidden medium. They were a direct statement about the nature of space and time themselves. This is often how major shifts in physics happen. It's not through a single flash of new data. It's through someone finally asking why the existing data looks the way it does, instead of just patching around it. In 1905, Albert Einstein published a paper that didn't try to save the ether. Instead, he threw it out entirely, along with the assumption that space and time were separate and absolute. Einstein started from two simple statements. First, the laws of physics look the same to every observer moving at a constant velocity. Nobody's viewpoint is special. Second, the speed of light in a vacuum is the same for every observer, regardless of how fast that observer is moving or in what direction. That second statement sounds harmless, but follow it carefully, and it destroys the Newtonian universe. Imagine you're standing still on a platform, and a train speeds past you at a significant fraction of the speed of light. A passenger on the train shines a flashlight forward. Under Newton's rules, you on the platform should measure that light moving at the speed of light plus the speed of the train. But Einstein's second postulate says, no. You measure it moving at exactly the speed of light. That's the same number the passenger on the train measures, not 1 kilometer per second faster. For both of those statements to be true at once, something else has to give. Something in the very structure of space and time has to bend to keep the speed of light constant for everyone. And that something is time itself, along with distance itself. Einstein worked out that observers moving relative to each other will disagree about how much time has passed between two events. They will also disagree about the distance between 2 points in space, not because their instruments are broken, not because of some illusion, but because time and distance are not fixed, universal quantities. They depend on how you're moving. Let's build up why this happens. It isn't magic. It follows directly from that one constant, the speed of light. Picture a simple clock made of nothing but a photon of light bouncing between two mirrors, one on the floor of a spaceship, one on the ceiling. Each time the photon completes a round trip, that counts as one tick. If you're standing inside that spaceship, you see the photon travel straight up and straight down, a simple vertical path. But now imagine someone watching that same spaceship fly past them at high speed. From their point of view, the photon isn't just moving up and down. The whole ship is also moving sideways. So the photon has to travel a longer, diagonal path to complete the same bounce. Here's the key point. The speed of light is fixed for both observers. If the outside observer sees the photon traveling a longer path, but at the exact same speed, then that trip has to take more time from their perspective. The moving clock, watched from outside, ticks slower than the same clock would tick for someone riding along with it. This effect is called time dilation, and it isn't an illusion or a trick of perception. Every observer, using perfectly functioning instruments, genuinely measures moving clocks running slow. The faster something moves relative to you, the slower its time passes, from your point of view. At everyday speeds, this effect is tiny. Walking, driving, even flying in an airplane, it's almost impossible to notice without extraordinarily precise instruments. But it isn't zero, and it has been measured directly. In 1971, physicists Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial airliners. They then compared them to identical clocks that stayed on the ground. The eastward flight came back, showing the clocks had lost about 59 nanoseconds. The westward flight came back, showing the clocks had gained about 273 nanoseconds. Both results matched Einstein's predictions almost exactly. Muons offer an even more dramatic confirmation. They're unstable subatomic particles created when cosmic rays strike Earth's upper atmosphere. A muon, at rest, survives for an average of about 2/millionths of a second before decaying. At that lifespan, even traveling near the speed of light, muons shouldn't be able to cross the distance from the upper atmosphere down to the ground before falling apart. And yet, detectors on the surface pick them up constantly. The reason is time dilation. From Earth's point of view, the muon's internal clock is running slow because the muon is moving so fast. That gives it far more time to reach the ground than its own resting lifespan would allow. Time dilation isn't a theoretical curiosity. It's something that shapes measurable particle physics happening above your head right now. Alongside time dilation comes a partner effect, length contraction. Just as moving clocks run slow from an outside perspective, moving objects appear shortened along their direction of motion. A spaceship traveling near the speed of light would appear compressed to an observer watching it fly past. Anyone riding inside, though, would notice nothing unusual about their own ship at all. Both effects come from the exact same source. It's the requirement that light speed stays fixed for every observer, forcing space and time to flex around that constant. This is where the phrase relativity of simultaneity comes in, and it might be the strangest consequence of all. Newton assumed that if two events happen at the same moment for one person, they happen at the same moment for everyone, everywhere. Einstein showed that isn't true. Picture a train moving at high speed, with a light positioned exactly in the middle of one of the carriages. At the instant the light flashes, it sends light toward both the front and back walls of the carriage simultaneously. A passenger sitting in the middle of the carriage sees the light hit both walls at the same time. That's because the walls are equal distances away, and light travels at a fixed speed. But someone standing outside on the platform, watching the train go by, sees something different. From their perspective, the train is moving forward. So the back wall is rushing toward the point where the light was emitted, while the front wall is moving away from it. The light reaches the back wall first, then reaches the front wall slightly later, as far as the platform observer is concerned. Two events that were simultaneous for the passenger on the train are not simultaneous for the person on the platform. Neither observer is wrong. There is no hidden true answer about which event really happened first. Simultaneity itself, the very idea of two things happening at the same time, depends on how you're moving. This single fact quietly demolishes the Newtonian idea of a universal, ticking clock shared by everyone in existence. There is no master clock. There's only your clock and my clock and countless other clocks. Each one is valid. Each one disagrees slightly with the others, depending on our relative motion. So if space isn't absolute and time isn't absolute, what is left that everyone can agree on? This question was answered not by Einstein himself at first, but by his former mathematics professor, Hermann Minkowski. In 1908, Minkowski gave a lecture where he made a statement that has echoed through physics ever since. He said that space by itself and time by itself are doomed to fade away into mere shadows. Only a union of the two, he said, will preserve an independent reality. Minkowski had realized something remarkable buried inside Einstein's equations. Observers disagree about distances, and they disagree about durations. But there is a specific combination of space and time that every observer calculates identically, no matter how they're moving. It's called the space-time interval. Think of it loosely as a four-dimensional version of distance. It blends the three familiar dimensions of space with a fourth dimension, time, into a single geometric object. Two events in the universe, say a firework exploding here and another firework exploding somewhere else a moment later, are separated by a certain amount of space and a certain amount of time. Different observers, moving at different speeds, will disagree about how much of that separation is space and how much is time. One observer might say the two fireworks were far apart and close together in time. Another might say they were closer together in space, but more spread out in time. But when you combine the space part and the time part, using Minkowski's particular mathematical recipe, everyone gets the exact same number for the interval between those two events. That number, the space-time interval, doesn't care how you're moving. It's the one thing that stays fixed, the one true, invariant quantity in a universe where space and time separately are fluid and observer-dependent. Minkowski gave physicists a powerful visual tool for picturing all of this, now called a space-time diagram. Imagine a simple graph with the usual spatial direction running left to right, and time running up the vertical axis instead of a second spatial direction. An object sitting perfectly still would trace a straight vertical line on this diagram. It moves through time without moving through space at all. An object moving at a constant velocity traces a diagonal line called its world line. The line tilts away from vertical by an amount that depends on its speed. Faster objects tilt closer and closer to a 45-degree angle, which represents the path of light itself, the fastest possible tilt any world line can have. Every object in the universe traces out its own world line through this four-dimensional diagram. Every planet, every person, every photon has one. It's a complete record of everywhere that object has ever been and every moment it has ever existed, all stitched together into a single continuous path. Two observers moving at different velocities relative to each other are, in this picture, essentially looking at the same four-dimensional diagram from different angles. It's the same way two people standing in different spots in a room see the same objects from different perspectives. Just as rotating your viewpoint in ordinary three-dimensional space changes how much of an object's width and depth you perceive, without changing the object itself, changing your velocity does something similar. It effectively rotates your perspective within space-time. It changes how much of an event's separation you perceive as space and how much you perceive as time, without changing the event itself or the invariant interval separating it from any other event. This is, in many ways, the cleanest possible way to understand why simultaneity is relative. It's the same way you can understand why moving clocks tick slow and why moving objects appear contracted. All three effects are, geometrically speaking, exactly the same kind of thing. Think of a tilted ruler, viewed from an angle. It appears to take up less horizontal space on a piece of paper than the same ruler viewed straight on, even though the ruler itself never actually changed length. Reactions to this new picture of the universe, when Einstein first proposed it, were far from unanimously enthusiastic. Many physicists were comfortable with 2 centuries of Newtonian success. They were deeply skeptical of a theory that seemed to abandon common sense entirely. It insisted that simultaneity, distance, and duration all depended on how fast you happened to be moving. Even Einstein himself never received the Nobel Prize in Physics specifically for relativity. That's despite it being widely regarded, even at the time, as his most significant achievement. The Nobel Committee was wary of the ongoing scientific controversy surrounding relativity. They were cautious about awarding a prize for a theory some prominent physicists still considered unproven. Instead, they awarded Einstein the 1921 Nobel Prize in Physics for his explanation of the photoelectric effect. That was a separate, more experimentally settled piece of work involving the quantum nature of light. It took years of accumulating evidence before the unification of space and time moved from controversial new idea to thoroughly confirmed framework. The bending of starlight during the 1919 eclipse helped. So did the precise match with Mercury's orbit and later decades of laboratory tests. Today, general relativity and special relativity aren't treated as bold, unproven speculation. They're treated as reliable, load-bearing infrastructure. Satellites, particle accelerators, and precision timekeeping systems all depend on their predictions being correct. Not approximately correct. Correct to many decimal places. There's a small but important detail hiding inside the mathematics of the space-time interval worth understanding. It explains why the speed of light keeps showing up everywhere in this story, from Michelson and Morley's failed experiment to Minkowski's geometric fusion of space and time. Space is naturally measured in units like meters or kilometers. Time is naturally measured in units like seconds. You can't directly add a distance to a duration, any more than you could meaningfully add a number of apples to a number of oranges, without first converting them into some shared, common unit. The speed of light, that fixed, unchanging number every observer agrees on, turns out to be exactly the conversion factor needed. It translates a duration of time into an equivalent distance of space and back again. Multiply a length of time by the speed of light, and you get a distance. Specifically, it's the distance light itself would travel during that time. That's precisely why astronomers casually measure vast cosmic distances using a unit called a light year, the distance light travels in 1 year. They're quietly treating a duration and a distance as interchangeable, expressed in the exact same fundamental unit. This is not a convenient coincidence or a notational trick. It's a direct reflection of the fact that space and time are not two separate categories of quantity that merely happen to relate to each other. They are two aspects of one single quantity, space-time, measured using a shared currency. The speed of light serves as the fixed, universal exchange rate between them. This is why the equation many people recognize without fully understanding it. Einstein's famous E equals mc squared also has the speed of light built directly into it. It relates energy and mass. That same conversion factor between space and time also governs the deep relationship between mass and energy. It's another consequence of treating space, time, mass, and energy as facets of one interconnected, unified framework, rather than as separate, independent quantities floating loosely alongside each other. This is the real meaning of the phrase, space-time is fundamental. Space and time aren't fundamental on their own. They're more like shadows cast by a four-dimensional object, space-time. The exact shape of the shadow you see depends on the angle you're standing at, meaning your velocity. Rotate your perspective by moving faster or slower, and the shadow changes shape. More space here, less time there. But the object casting the shadow never changes. This four-dimensional way of thinking also cleans up something that used to seem mysterious, the question of cause and effect. Picture every event in the universe as a single point in this four-dimensional space-time, a location defined by 3 coordinates of space and 1 of time. From any given point, you can ask which other points it's possible to influence, and which points could have influenced it. Because nothing can travel faster than light, the answer forms a very specific shape, called a light cone. Imagine a flash of light released from a single point, expanding outward in all directions as a sphere that grows larger every moment. Plotted across time, that expanding sphere traces out a cone shape, widening as time moves forward. Everything inside that forward cone is a place and moment that this event could still affect, using signals or objects traveling at or below the speed of light. Everything inside a matching cone pointing backward in time represents everything that could have influenced this event. Everything outside both cones is simply out of reach. It's disconnected from that event, both in the past and future, because reaching it would require traveling faster than light. This structure, this network of light cones, stitched together across the universe, is the actual skeleton of cause and effect. It only makes sense as a structure in unified space-time. If you tried to describe it using separate, absolute space and separate, absolute time, the whole picture falls apart. Different observers would disagree about which events even happened before others. In space-time, causality is protected precisely because the geometry itself prevents effects from happening before their causes. That's true for any observer, moving in any direction, at any speed. Consider a concrete example, a star going supernova in a distant part of the galaxy, thousands of light years away. The explosion itself is an event, a specific point in space-time, with its own light cone spreading outward from it. Anyone standing close enough to that star to see it explode in real time sits inside that event's immediate future light cone. But Earth, thousands of light years away, does not. Earth sits far outside the reach of that event until enough time has passed for light to actually cross the distance and arrive. This means that when astronomers on Earth finally see that supernova appear in the night sky, they aren't seeing something that just happened. They're seeing something that happened thousands of years ago. There was no way, no signal, no method of any kind for anyone on Earth to have known about that explosion any sooner. Nothing, not light, not gravity, not any form of information, can outrun the expanding boundary of that event's light cone. Different observers, moving at different velocities, might disagree about exactly how much time passed between the explosion and its light reaching Earth. They might even disagree about exactly which distant events counted as simultaneous with the explosion. But every single observer will agree completely on the one thing that actually matters for cause and effect. The explosion could not possibly have influenced anything on Earth before its light had time to arrive. That boundary, the light cone itself, is the same fixed, invariant structure for everyone. It's carved directly into the unified geometry of space-time, rather than into any one observer's particular, shifting sense of space and time separately. Everything so far has been about space-time in the absence of gravity, what physicists call flat space-time or special relativity. But Einstein wasn't finished. For about a decade after 1905, he wrestled with a nagging problem. How does gravity fit into this new picture? Newton had described gravity as a force, an invisible pull reaching instantly across space between any two masses. But Einstein's own theory said nothing, not even a force, could travel faster than light. If the sun suddenly vanished, Newton's gravity would mean Earth instantly flies off in a straight line the moment it happens. Einstein's framework said that couldn't be right. The effect couldn't outrun light itself. The breakthrough came from a simple thought experiment, one Einstein later called the happiest thought of his life. Imagine a person falling freely in an elevator with its cable cut, or an astronaut floating in orbit. That person feels weightless. They cannot tell the difference between falling freely near a massive planet and simply floating in empty space, far from any gravity at all. That's true using any experiment performed entirely inside their falling elevator. Einstein pushed this thought experiment further. He imagined a windowless rocket accelerating through empty space, far from any planet or star. Someone standing inside that accelerating rocket would feel pressed against the floor, exactly the way you feel pressed against the ground by Earth's gravity. There would be no experiment they could perform, entirely from inside the sealed rocket, that could tell them whether they were sitting on a planet's surface or accelerating through empty space. This is called the equivalence principle. It's the idea that gravity and acceleration are, locally, indistinguishable from one another. Einstein then asked what would happen if a beam of light entered the accelerating rocket through a small hole in one wall. As far as an outside observer watching from a fixed position is concerned, that light travels in a perfectly straight line. Because the rocket is accelerating upward while the light crosses it, the point where the light exits on the opposite wall will have shifted slightly. That means, to someone standing inside the rocket, the light beam appears to curve downward slightly as it crosses the cabin. It bends, as though a gravitational field were pulling on it. The equivalence principle says acceleration and gravity are indistinguishable. So this thought experiment forced Einstein to a striking conclusion. Light itself, despite carrying no mass, must also bend when passing through a genuine gravitational field. That's not because gravity directly pulls on light the way it pulls on a thrown ball. It's because gravity curves the very geometry that the light, like everything else, has no choice but to follow. This was the theoretical seed that eventually led to the prediction confirmed by Eddington's eclipse expedition years later: starlight bending as it passed near the sun. That wasn't because the sun was reaching out and grabbing photons. It was because the sun's mass had curved the space-time those photons were traveling straight through. Gravity, Einstein realized, isn't quite like other forces. It doesn't push or pull so much as it changes the geometry that everything moves through. This became the core idea of general relativity, published in 1915. Mass and energy don't create a force that reaches across a flat, unchanging space-time. Mass and energy curve space-time itself. Objects moving through curved space-time simply follow the straightest possible path available to them, called a geodesic. Because the space they're moving through is curved, that straightest path looks, to us, like a curved orbit or a falling trajectory. A famous way to picture this is a heavy ball placed on a stretched rubber sheet, creating a dip. Smaller balls roll around it in curved paths. That's not because something is pulling them sideways, but because the sheet itself is bent beneath them. It's an imperfect picture, since space-time has 4 dimensions, not 2, but it captures the core idea. Mass tells space-time how to curve, and curved space-time tells mass how to move. This single reframing solved problems Newton's gravity couldn't touch. Mercury, the planet closest to the Sun, has an orbit that slowly rotates over time, a phenomenon called the precession of its perihelion. Newton's equations predicted most of this rotation, but fell short by a small, persistent amount. The gap was about 43 arc-seconds per century, a tiny discrepancy that puzzled astronomers for decades. Einstein's general relativity, with no adjustable parameters, predicted that exact missing amount. It was one of the first great confirmations that gravity really is curved space-time, not a Newtonian force acting across a flat, separate stage. General relativity also predicted that light itself, though massless, should bend as it passes near a massive object. That's because light, too, must follow the curved geometry of space-time. In 1919, astronomer Arthur Eddington led an expedition to observe a solar eclipse. He measured the positions of stars whose light passed close to the sun. The starlight bent by exactly the amount Einstein's equations predicted. It made headlines around the world and turned Einstein into a global celebrity almost overnight. Getting from the happiest thought of his life to a finished working theory took Einstein nearly a decade of extraordinarily difficult work, and he didn't do it alone. Describing curved space mathematically required tools far beyond the algebra and calculus used in ordinary physics at the time. The branch of mathematics he needed was called differential geometry. It had largely been developed decades earlier by mathematician Bernhard Riemann for entirely different, abstract purposes, with no expectation it would ever describe the physical universe. Einstein struggled with this unfamiliar mathematics for years. He later credited his close friend and former classmate, mathematician Marcel Grossmann, with helping him learn and apply the necessary geometric tools. One key tool was a mathematical object called a metric tensor. It describes exactly how distances and durations are measured at every single point within a curved space-time. Working through failed attempts, incorrect equations, and significant frustration, Einstein finally arrived at his complete field equations in November of 1915. They're a compact but extraordinarily rich set of equations relating the curvature of spacetime directly to the distribution of mass and energy within it. Written in its most condensed form, the equation looks deceptively simple. But each term represents an enormous amount of geometric information. It encodes, in principle, the complete gravitational behavior of any arrangement of mass and energy anywhere in the universe. One of the clearest, most direct confirmations of what those field equations actually predict about time came not from space at all, but from a basement at Harvard University. In 1959, physicists Robert Pound and Glenn Rebka set up an experiment in a tower just 22.5 meters tall. They measured the tiny shift in the frequency of gamma-ray photons as they traveled from the bottom of the tower to the top. General relativity predicts that a photon climbing away from a massive object should lose a tiny, precise amount of energy, even over a distance as small as 22 meters on the surface of Earth. Its frequency shifts downward because it's effectively climbing out of a gravitational well. Time itself runs at a very slightly different rate at the bottom of the tower compared to the top. Using an extremely sensitive technique involving the vibration of radioactive atoms, Pound and Rebka measured this frequency shift directly. It matched Einstein's prediction to within about 1%. That's an astonishing level of precision for an effect that small, achieved without ever leaving the ground. This experiment proved that gravitational time dilation isn't some exotic effect, only relevant near black holes or distant stars. It's happening continuously, right here on Earth, at a scale of just a couple dozen meters. It's a direct, measurable demonstration that time genuinely runs at different rates, depending on how deep you are within a gravitational field, even a field as comparatively weak as Earth's own. One of the most striking predictions of general relativity is gravitational time dilation. And this is where the union of space and time becomes something you can actually verify with a device sitting on your kitchen counter. If mass curves spacetime, and time is part of spacetime, then mass should also affect the rate at which time itself passes. Specifically, clocks closer to a massive object run slower than clocks farther away, since they're deeper in its gravitational field. This isn't the same effect as velocity-based time dilation from earlier. It's a separate consequence of the same underlying idea that space and time are one unified fabric that mass can bend. You experience this effect constantly, whether you realize it or not. A clock at sea level runs very slightly slower than a clock at the top of a mountain, because the clock at sea level is deeper in Earth's gravitational well. The difference is minuscule in daily life, but it becomes critically important for a piece of technology billions of people rely on. The Global Positioning System. GPS satellites orbit roughly 20,000 kilometers above Earth's surface, moving at speeds of about 14,000 kilometers per hour. 2. Competing relativistic effects act on their onboard atomic clocks. Their high orbital speed causes their clocks to run slower, from Earth's perspective, by about 7 microseconds per day. That's due to velocity-based time dilation. But their greater distance from Earth means they sit in a weaker part of Earth's gravitational field. That causes their clocks to run faster, due to gravitational time dilation, by about 45 microseconds per day. Combine both effects, and the satellite clocks run fast overall. They gain about 38 microseconds every single day compared to clocks on the ground. That sounds like nothing. But GPS positioning relies on comparing extremely precise timing signals to calculate your location, and the speed of light means even tiny timing errors translate into large position errors. Without correcting for this relativistic drift, GPS location errors would accumulate at a rate of roughly 10 kilometers per day. That would render the entire system useless within minutes. Engineers correct for this by deliberately adjusting the satellite clocks before launch. They tune them to tick slightly slower than ground clocks, so that once relativity does its work in orbit, they end up synchronized correctly. Every time your phone shows your location accurately, general relativity and the unified nature of space-time is quietly working behind the scenes to make that possible. There's another elegant test of curved space-time proposed by physicist Erwin Shapiro in 1964, involving nothing more exotic than bouncing radar signals off other planets. If space-time is curved by mass, a radar signal passing close to the Sun on its way to another planet, say Venus or Mercury, should take very slightly longer to complete its journey than a signal that doesn't pass near the Sun. The signal is traveling through space that has been stretched and curved by the Sun's mass, effectively lengthening the path it has to cross. Time itself also runs slightly slower, deeper in that gravitational well. This extra travel time is called the Shapiro delay. It's tiny, on the order of a couple hundred microseconds for a round trip to a nearby planet, but it's precisely measurable using radar astronomy. Experiments bouncing radar signals off Venus and Mercury confirmed the predicted delay to extraordinary precision. Later, experiments used signals from spacecraft like the Cassini probe on its way to Saturn. These matched general relativity's prediction to within about 0.002%. Mercury's orbit, the bending of starlight, gravitational redshift measured in a basement, GPS satellite corrections, and radar signals delayed by the Sun's curvature all come from the exact same underlying equations. They describe the exact same unified fabric of space-time. Every single one of them has matched observation, with no exceptions found in over a century of increasingly precise testing. Gravitational redshift was also confirmed astronomically, using an object far more extreme than anything found on Earth, a companion star to Sirius, the brightest star in the night sky, called Sirius B. Sirius B is a white dwarf, the extremely dense, collapsed remnant of a star roughly the mass of the Sun. It's compressed down to a size not much larger than Earth, giving it a surface gravity tens of thousands of times stronger than our planet's. In the 1920s, astronomers measured a small but definite redshift in the light coming from Sirius B. It exactly matched the amount general relativity predicted for light escaping a gravitational field that strong. This offered one of the earliest astronomical rather than laboratory confirmations that mass genuinely warps the passage of time. It's not merely a small correction, it scales up dramatically with the strength of gravity involved. There's a deeper mathematical reason why unifying space and time turns out to matter so much. It's connected to a discovery made by mathematician Emmy Noether in 1915, around the same time Einstein was finishing general relativity. Noether proved a remarkable general theorem. Every continuous symmetry in the laws of physics corresponds to a conserved quantity, something that stays constant throughout any physical process. If the laws of physics don't change, depending on where in space you are, that symmetry corresponds directly to the conservation of momentum. If the laws of physics don't change, depending on which direction you're facing, that symmetry corresponds to the conservation of angular momentum. And if the laws of physics don't change depending on when in time an experiment is performed, That symmetry corresponds directly to the conservation of energy. It doesn't matter whether the experiment happens today, yesterday, or 1,000 years from now. This means energy conservation, one of the most fundamental, reliable principles in all of physics, is directly tied to the structure of time itself. Time, treated as a dimension within space-time, behaves uniformly. There are no special, privileged moments built into the laws of nature. Space and time are unified into a single geometric structure. So the symmetries, producing conservation of momentum and conservation of energy, aren't really separate ideas either. They're different facets of the same broader symmetry of space-time as a whole, called Poincare symmetry. It includes shifts in position, shifts in time, rotations, and the specific way velocities transform between observers, all wrapped into one unified mathematical structure. This is yet another way of seeing that space and time were never truly separate ingredients to begin with. Even the conservation laws that make rockets work, that keep planets orbiting predictably, that let engineers calculate exactly how much fuel a mission needs, are secretly statements about the combined symmetry of a single four-dimensional space-time. They're not two independent sets of rules for space and for time running in parallel. Gravitational time dilation gets far more extreme as mass and density increase, and nowhere is that more dramatic than near a black hole. A black hole forms when an extraordinarily massive object collapses down into an incredibly small volume. It curves space-time so sharply that beyond a certain boundary, called the event horizon, nothing, not even light, can escape. As you approach the event horizon of a black hole, the gravitational time dilation effect grows without bound. To a distant observer, watching something fall toward a black hole, that object appears to move slower and slower as it nears the horizon. Its light stretches to longer wavelengths. Its clock appears to tick more and more slowly. Mathematically, from the outside observer's point of view, the object never quite finishes crossing the horizon. It appears frozen there, fading from view as its light grows dimmer and redder. But it never technically disappears entirely from an outside vantage point. But here's the part that really drives home how deeply space and time are tangled together. From the perspective of someone actually falling into the black hole, nothing strange happens as they cross the event horizon. At least, not immediately, and not because of any barrier. They cross it in finite time, according to their own clock, feeling nothing unusual at that specific boundary. What awaits them afterward, though, is where the fusion of space and time becomes almost impossible to describe without the mathematics. Inside the event horizon, the roles of space and time effectively swap. Outside a black hole, you can move freely through space in any direction. But time only moves one way, forward, no matter what you do. Inside the event horizon, the direction toward the center, called the singularity, stops being a direction you could choose to avoid. It's the same way you can't choose to avoid moving forward in time out here. Falling toward the singularity inside a black hole becomes as unavoidable as aging is out here. That's not because some force is dragging you. It's because the geometry of space-time itself has rotated in a sense, turning what used to be a spatial direction into something with the same unavoidable, one-way character that time has for us. This is one of the clearest possible demonstrations that space and time aren't separate categories at all. They are aspects of one single geometric structure. In extreme enough conditions, the labels we usually put on, which is which, can shift entirely. For most of the century, Since black holes were first predicted mathematically, they remained purely theoretical objects. They were inferred indirectly from their gravitational influence on nearby stars and gas, never seen directly. That changed in 2019. The Event Horizon Telescope collaboration is a global network of radio telescopes effectively combined into a single instrument the size of Earth itself. They released the first direct image of a black hole's shadow, the supermassive black hole at the center of the galaxy, M87, roughly 6.5 billion times the mass of the Sun. The image showed a dark central region, the shadow cast by the event horizon against the glowing, superheated gas swirling around it. It was surrounded by a bright ring of light, bent around the black hole by its own curved space-time. That's a direct visual confirmation of the extreme gravitational lensing. General relativity predicts in exactly this kind of environment. In 2022, the same collaboration released an image of the supermassive black hole at the center of our own galaxy, called Sagittarius A, roughly 4 million times the mass of the Sun. It confirmed that the object long suspected to sit at the Milky Way's center behaves exactly as general relativity predicts a black hole should. There's also a strange, quiet postscript to the story of black holes. It connects general relativity back to the unresolved tension with quantum mechanics mentioned earlier. In 1974, physicist Stephen Hawking showed that black holes shouldn't be perfectly black after all, once quantum effects near the event horizon are taken into account. They should very slowly emit a faint stream of particles, now called Hawking radiation. They gradually lose mass and energy over unimaginably long timescales. For any black hole formed from a collapsing star, this evaporation is so slow that it would take vastly longer than the current age of the universe to have any noticeable effect. But the prediction itself, treating space-time near the event horizon quantum mechanically rather than purely geometrically, remains one of the most important theoretical clues physicists have in the ongoing search for a theory that successfully merges gravity with quantum mechanics. Let's step back to something a little more grounded, a puzzle called the twin paradox. It shows how the unification of space and time produces real, physical, lasting consequences, not just abstract disagreements about clocks. Imagine two twins. One stays on Earth. The other boards a spacecraft and travels to a distant star at a significant fraction of the speed of light, then turns around and comes back. According to time dilation, the traveling twins' clock runs slow relative to Earth throughout most of the journey because of their high velocity. When the traveling twin returns, they find that less time has passed for them than for their twin who stayed behind. The twin who traveled has aged less. This isn't a hypothetical curiosity. It has been effectively tested using precise atomic clocks flown on aircraft and spacecraft, always matching the predicted difference. For years, this scenario tripped people up. From the traveling twins' point of view, wasn't it Earth that moved away and came back? Shouldn't the effect be symmetrical? The resolution lies in the fact that the situation isn't actually symmetrical at all. The twin who stays on Earth moves through space-time at a constant velocity the entire time, following a straight path through space-time. The traveling twin has to accelerate to leave Earth. They have to turn around at the distant star and decelerate upon return. That breaks the constant velocity that would make their situation match their siblings. That acceleration marks a real, physical difference between the two paths through space-time, not just a difference in perspective. And Here's the elegant part. When you calculate the total space-time interval, the four-dimensional length, along each twin's path through space-time, the paths are genuinely different lengths. The traveling twin's path is measured to be shorter in terms of the time experienced along it. That's why they age less. This isn't a paradox. Once you accept that space and time form a single combined geometry, different paths through that geometry, just like different paths through ordinary three-dimensional space, can have different lengths. Time isn't a universal beat, playing the same for everyone. It's a measurement of the particular path you personally took through the four-dimensional fabric of the universe. This isn't only a thought experiment involving imaginary spacecraft traveling near light speed. It has played out, in miniature, with real human beings. Astronaut Scott Kelly spent 340 days aboard the International Space Station. His identical twin brother, Mark Kelly, also an astronaut, remained on the ground. NASA took the rare opportunity to study the two of them closely, comparing everything from their gene expression to their gut bacteria. As a small but genuine footnote to that research, physicists calculated the relativistic time difference between the twins. The International Space Station orbits at roughly 28,000 kilometers per hour. Velocity-based time dilation makes Scott's clock run slightly slower than Mark's. That effect dominates over the very slight opposing gravitational time dilation caused by being farther from Earth's center at orbital altitude. Combine both effects, and over his time in orbit, Scott Kelly returned to Earth having aged a few milliseconds less than his twin brother would have if Mark had stayed in orbit too. It's a genuinely measured, real-world example of the exact same effect that separates the twins in the classic thought experiment. It's just scaled down from years to milliseconds, because orbital speeds are so much slower than a significant fraction of light speed. It is a small number, but it is not imaginary or theoretical. It is a real difference between two real people. It's caused by nothing more than one of them spending time moving faster relative to Earth than the other, exactly as the unified structure of space-time predicts. If space-time is a real physical fabric and not just a mathematical bookkeeping trick, then it should be able to do something a genuine physical medium does. It should be able to ripple. Einstein predicted exactly this in 1916. Shortly after finishing general relativity, imagine two extremely massive objects, say a pair of black holes, orbiting each other and eventually colliding. The violent, asymmetric motion of all that mass should send ripples outward through space-time itself, stretching and squeezing space as they pass. It's the same way ripples spread outward across a pond after a stone breaks the surface. These ripples are called gravitational waves. Einstein himself doubted they would ever be detected. He calculated that even a cataclysmic event, like two black holes merging, would produce a wave so weak by the time it reached Earth that it would stretch and squeeze space by a fraction smaller than the width of a proton. For 100 years, that prediction sat there, mathematically sound, but seemingly impossible to confirm. Then, in September of 2015, an instrument called LIGO detected one. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. It works by splitting a laser beam and sending the two halves down two perpendicular tunnels, each 4 kilometers long. The beams bounce off mirrors and recombine to check whether the two paths are still exactly the same length. A passing gravitational wave stretches one tunnel by an almost unimaginably tiny amount while squeezing the other. That throws the recombined beams very slightly out of alignment. The signal LIGO detected came from two black holes, each tens of times the mass of the Sun, spiraling into each other and merging over a fraction of a second. That event had taken place about 1.3 billion years ago. Its ripple finally washed over Earth and was caught by instruments built specifically to listen for it. The distortion LIGO measured was smaller than 1,000th the width of a proton, spread across a 4-kilometer tunnel. It matched Einstein's century-old prediction almost perfectly. This discovery did more than confirm a 100-year-old equation. It proved, directly and physically, that space-time is not an abstract mathematical convenience. It is something with genuine physical properties, something that can vibrate, carry energy, and be measured. That's exactly the way a unified, real fabric of space and time should behave. Since that first detection, dozens of additional gravitational wave events have been recorded, including collisions between neutron stars. That gives astronomers an entirely new way of observing the universe that has nothing to do with light at all. They're listening instead to the vibrations of space-time itself. Massive objects don't just curve space-time, they can also drag it around with them if they're spinning, an effect called frame dragging. Imagine space-time not as a static rubber sheet, but as something closer to a thick, viscous fluid. A spinning object, like a rotating planet, star, or black hole, doesn't just create a dip in that fabric. It partially drags the surrounding space-time along with its rotation. It's the way a spinning ball dropped into honey would twist the honey around it as it turns. This effect was predicted by physicists Joseph Lenz and Hans Thöring in 1918. It's extraordinarily small for an object like Earth, but not so small that it's unmeasurable. In 2004, NASA launched a satellite called Gravity Probe B. It carried some of the most precise gyroscopes ever built into orbit around Earth, specifically to detect this dragging effect. Over the course of its mission, the gyroscope's orientation shifted by a tiny, measurable amount. It matched the frame dragging, predicted by general relativity, to within a small margin of error. Earth, simply by rotating, drags the fabric of space-time around itself, just slightly. It's the same way a rotating object dragging fluid around it would. Around a spinning black hole, this effect becomes vastly more extreme. A rotating black hole is described mathematically by a solution to Einstein's equations called the Kerr metric. It drags space-time around itself so violently that there's a region just outside the event horizon called the ergosphere, where space-time is being dragged around faster than light itself could resist it. Inside the ergosphere, it becomes physically impossible for any object to remain still relative to a distant observer, no matter how powerful its engines. The fabric of space itself is being swept along with the black hole's rotation. You aren't being pushed in the way a force pushes you. The space you're standing in is simply moving, carrying you with it, whether you want it to or not. That's yet another vivid demonstration that space is not a passive, empty backdrop. It's an active participant with its own physical behavior. Neutron stars offer another extreme laboratory for watching space-time's unified nature in action, sitting just short of full gravitational collapse into a black hole. When a massive star runs out of nuclear fuel, its core collapses. If the remaining core is between roughly 1.4 and about 3 times the mass of the Sun, The collapse halts not at a black hole, but at an object called a neutron star. A neutron star is so dense that a single teaspoon of its material would have a mass of roughly 1 billion tons. A neutron star typically has a mass comparable to the Sun, compressed into a sphere only about 20 kilometers across. Gravity at the surface of a neutron star is roughly 200 billion times stronger than gravity at Earth's surface. That's strong enough that gravitational time dilation becomes directly measurable, rather than the tiny microsecond corrections needed for GPS. A clock sitting on the surface of a neutron star would tick noticeably slower than a clock far away, by a fraction that can reach several tenths of a percent. That's an enormous difference by the standards of everyday gravitational time dilation. Many neutron stars also spin extraordinarily fast, some completing a full rotation in just a few milliseconds. That's fast enough that a point on their equator can be moving at a significant fraction of the speed of light. These rapidly spinning neutron stars are called pulsars. They sweep beams of radiation across space like a lighthouse. Because they rotate with such extreme precision, astronomers use them as some of the most accurate natural clocks in the universe. They're precise enough to test general relativity's predictions about time dilation and frame dragging with extraordinary sensitivity. Observations of pulsars orbiting each other in binary systems have confirmed, again and again, that the combined stretching and warping of space and time predicted by Einstein's equations matches what nature actually does. That includes the gradual loss of orbital energy as the system radiates gravitational waves, slowly spiraling the two neutron stars closer together, exactly as general relativity predicts. One of the strangest theoretical consequences of treating space and time as a single, flexible geometric fabric is the idea of a wormhole, a hypothetical shortcut connecting two distant points in space-time. In 1935, Einstein and physicist Nathan Rosen worked out a mathematical solution to the general relativity field equations, describing what's now called an Einstein-Rosen bridge. It's a kind of tunnel connecting two separate regions of space-time, or even two entirely separate universes, through a throat-shaped passage. On paper, the geometry works. Space-time can, in principle, be bent and connected in this way without violating the mathematics of general relativity. In practice, every known solution describing a wormhole like this turns out to be either unstable, collapsing and pinching shut faster than anything, even light, could cross it. Or it would require a form of matter with negative energy density to prop it open, something that has never been observed to exist in any usable quantity. Wormholes remain, for now, a fascinating mathematical possibility rather than a demonstrated feature of the real universe. But their very existence as a valid solution to Einstein's equations says something important. If space and time were genuinely separate, fixed, and absolute, the idea of physically connecting two distant points in space through a shortcut in time would be nonsensical. But space-time is a single, flexible, geometric object, capable of being curved, stretched, and in principle, even folded. The mathematics allows for these exotic connections to at least be written down and studied, even if building one may be permanently beyond reach. Some solutions to Einstein's equations go even further. They describe what are called closed time-like curves, paths through space-time that loop back on themselves, theoretically allowing an object to return to its own past. Physicist Stephen Hawking proposed what he called the chronology protection conjecture. It's the idea that the laws of physics, likely involving quantum effects not yet fully understood, probably prevent these loops from ever actually forming in reality, protecting the universe from paradoxes. Whether or not that conjecture is correct remains unresolved. But the fact that general relativity's equations even permit these strange possibilities to be explored mathematically is only possible because space and time are treated as a single, malleable structure rather than two separate, rigid categories. In 1949, logician Kurt Gödel, a close friend of Einstein's during their years together at the Institute for Advanced Study in Princeton, worked out an exact solution to Einstein's field equations. It described a hypothetical, uniformly rotating universe. In this universe, the overall rotation of all matter creates a large-scale frame-dragging effect so extreme that it produces genuine closed time-like curves throughout the entire universe. In Gödel's rotating universe, someone with a fast enough spacecraft could, in principle, travel out into space and return to their own past. They could meet an earlier version of themselves, all without ever violating a single local law of physics along the way. There's no strong evidence that our actual universe rotates in the way Gödel's solution describes. Current observations suggest the universe as a whole shows no significant overall rotation. But Gödel's solution remains mathematically valid, a real, permitted answer to Einstein's own equations. It deeply unsettled Einstein, who reportedly found it difficult to reconcile with his own intuitive sense of how time ought to behave, even though he could find no mathematical flaw in Gödel's reasoning. More recently, some theoretical physicists have proposed an even stranger possible connection, an idea nicknamed ER equals EPR. It links Einstein and Rosen's wormhole solution from 1935 with a completely different 1935 paper by Einstein, Boris Podolsky, and Rosen describing quantum entanglement. That's the phenomenon where two particles remain mysteriously correlated no matter how far apart they're separated. The speculative idea is still very much a subject of active theoretical research rather than settled physics. It suggests that entangled particles might, in some deep mathematical sense, be connected by an impossibly thin, unusable wormhole. That would mean the strange non-local correlations of quantum mechanics and the geometric shortcuts permitted by general relativity might ultimately be two different descriptions of the exact same underlying phenomenon. Nobody currently knows whether this idea is correct. But the fact that serious physicists are seriously exploring a connection between quantum entanglement and the geometry of space-time shows just how far-reaching the consequences of unifying space and time have turned out to be. It stretches from Einstein's original 1905 train and clock thought experiments all the way to the frontiers of unsolved, modern theoretical physics over a century later. Now, let's zoom all the way out. Space-time doesn't only bend locally near planets, stars, and black holes. It can stretch on a cosmic scale. This is where the union of space and time reveals perhaps its strangest consequence of all. In the 1920s, astronomer Edwin Hubble made a discovery that changed cosmology forever. Observing distant galaxies, he found that nearly all of them were moving away from us. The farther away a galaxy was, the faster it appeared to be receding. This became known as Hubble's law. The natural first interpretation was that galaxies are flying outward through space, the way debris flies outward from an explosion. But general relativity offers a more accurate and more strange description. The galaxies themselves aren't necessarily rocketing through a fixed, static space. Space itself, the distance between galaxies is expanding. Picture dots painted on the surface of a balloon, and then imagine inflating that balloon. Every dot moves farther away from every other dot. That's not because the dots are crawling across the balloon's surface, but because the surface itself, the space between them, is stretching. That's closer to what's actually happening across the universe on a much larger scale, and in 3 dimensions rather than 2. This means the redshift astronomers observe in distant galaxies, the stretching of light toward longer, redder wavelengths, isn't purely a Doppler effect from motion through space. It's not just like the way an ambulance siren changes pitch as it passes you. It's also, and largely, a stretching of the light's wavelength caused by the expansion of space itself while the light was traveling toward us. Space is not a passive container that things move through. It is an active, dynamic participant. It's capable of expanding, stretching, and even accelerating in how quickly it stretches. And because space and time are unified, this expansion has consequences for time as well. The rate at which the universe expands, and how that rate has changed throughout cosmic history, is itself described using space-time geometry. It's the same mathematics that governs black holes and orbiting planets, simply applied on the largest possible scale. This brings us to perhaps the single most mind-bending consequence of treating space and time as one unified structure. What happened, or rather, what didn't happen, before the Big Bang? Run the expansion of the universe backward in time, and galaxies get closer together. The universe gets smaller, denser, and hotter, all the way back toward a state of extremely high density, roughly 13.8 billion years ago. Under a purely Newtonian mindset, it feels natural to ask what happened before that moment. It's as if time were a river stretching infinitely in both directions, with the Big Bang simply marking a particular point along an already existing timeline. But space and time are unified into a single space-time structure. The Big Bang represents the origin of that very structure. So the question of what came before it may not even be meaningful in the way it sounds. If time itself is part of the fabric that came into being at the Big Bang, then asking what happened before, it can be a bit like standing at the North Pole and asking what's further north. North is a direction defined relative to the Earth's structure. Once you're standing at the northernmost point, the concept simply runs out of application. That's not because there's some mysterious barrier, but because the very framework that gave the word north meaning doesn't extend any further in that direction. Many physicists suspect something similar may apply to time at the Big Bang. Time, as a dimension of space-time, may have had a beginning rather than stretching back infinitely. This remains an active area of research. There are competing ideas, including proposals involving quantum gravity, cyclic models, and multiverse scenarios. None of them are settled science yet. But the mere fact that this question is even coherent, that time itself might have a boundary the way space has boundaries near a black hole's singularity, only makes sense once you accept one thing. Time isn't some separate, universal river flowing independently of everything else. It's a woven part of the same fabric as space. And fabric, unlike an eternal river, can have edges. There's a practical side effect of curved space-time that astronomers now use as a genuine scientific tool called gravitational lensing. Mass curves, space-time, and light follows that curvature. A massive object sitting between Earth and a more distant light source can bend the path of that background light. It acts something like a lens made of warped space rather than glass. This isn't a small effect around extremely massive objects, like entire galaxy clusters. Light from galaxies far behind, a massive cluster can be bent, magnified, and even split into multiple images. They arrive at Earth from several slightly different directions at once, all originating from the same single background source. In some particularly well-aligned cases, the background light gets smeared into a nearly complete circle around the foreground mass. This is called an Einstein ring, named for the man whose equations predicted this bending decades before astronomers had instruments sensitive enough to observe it. Astronomers now use gravitational lensing deliberately, treating massive foreground galaxy clusters as natural telescopes. They use their space-time curving mass to magnify and reveal extremely distant, faint galaxies that would otherwise be far too dim to detect with any telescope humanity has built. Some of the most distant galaxies ever observed were only visible because a massive foreground cluster happened to be curving space-time in just the right way to magnify their light. This technique also gives astronomers a way to measure the amount of matter in a foreground cluster, including invisible dark matter. They carefully measure exactly how much the background light has been bent, since the degree of bending depends directly on how much mass, visible or invisible, is curving the space-time the light passes through. Every one of these images, every ring, every arc, every duplicated galaxy scattered around a cluster is a direct visual demonstration of something important. Space is not empty, passive geometry. It is something with real curvature that light itself must obey. Push the story of space-time back to the very beginning, to a period so early in the universe's history that it's measured in fractions of a second, almost too small to write out meaningfully. You find one of the most dramatic stretching events space-time has ever undergone. In the earliest moments after the Big Bang, cosmologists believe the universe underwent an extraordinarily rapid period of expansion called cosmic inflation. First proposed by physicist Alan Guth in 1980. During inflation, space-time is thought to have expanded by a factor of at least 10, followed by roughly 26 zeros. That happened in a period of time lasting somewhere around 10 to the negative 32 seconds, an amount of time so brief it defies ordinary intuition entirely. To put the scale of that stretching into perspective, inflation is thought to have taken a region of space far smaller than a single atom and expanded it, in a fraction of a second, to a size larger than a grapefruit. It kept going from there as ordinary cosmic expansion took over afterward. Inflation wasn't proposed just for the sake of drama. It solves several genuine puzzles that had troubled cosmologists. Without it, distant regions of the universe, too far apart to have ever exchanged light or influence, shouldn't share the same temperature and density to the precision astronomers actually observe. Inflation explains this by proposing that those regions were, in fact, in close contact before the rapid stretching, sharing properties while still connected. They were then flung far apart from each other, faster than light could have kept them in contact afterward. That's a permissible outcome, because it's the stretching of space itself carrying those regions apart, not any object moving through space faster than light, which relativity still forbids. This distinction matters enormously, and it's only coherent because of the unified nature of space-time. Nothing is allowed to move through space faster than light. But space itself, the fabric between 2 points, is not bound by that same speed limit. It can expand at any rate, carrying galaxies apart from each other faster than light, without a single photon or particle ever exceeding the speed limit locally. This is exactly why extremely distant galaxies can currently be receding from us faster than light. That fact sounds like it violates relativity, but it doesn't. It's the space between us and them stretching, not those galaxies physically flying through space at impossible speeds. That same expansion of space, the stretching first noticed by Hubble, hasn't been slowing down the way early cosmologists expected it should. They expected gravity to be pulling everything back together and gradually breaking the expansion. In the late 1990s, two independent teams of astronomers were studying distant exploding stars called Type 1, a supernovae, which reliably produce a known amount of light. They discovered something startling. The expansion of the universe is accelerating, not slowing down. Something is actively pushing space apart, stretching it faster and faster as time goes on. Physicists gave this mysterious influence a name, without yet understanding exactly what it is, calling it dark energy. The leading explanation treats dark energy as a property of space itself, an energy inherent to the vacuum. It's sometimes associated with a term Einstein originally introduced into his own equations decades earlier, called the cosmological constant. He added it to allow for a static universe, and later reportedly called it his greatest blunder, once Hubble showed the universe wasn't static at all. It's a strange twist that the term Einstein once regretted adding may turn out to describe something genuinely real. It's an intrinsic energy woven into empty space that grows in total influence as space itself grows larger, since more space simply means more of this vacuum energy pushing outward. Roughly 68% of all the energy in the universe, based on current measurements, appears to exist in this form. It outweighs ordinary matter and dark matter combined. This accelerating expansion has consequences for the long-term fate of space-time itself. If dark energy continues behaving the way current measurements suggest, distant galaxies will eventually recede from us so quickly that their light will never be able to reach us again. They'll gradually vanish from our observable universe, one by one, over trillions of years, leaving any future observers in the Milky Way looking out at an increasingly dark, isolated sky. In more extreme scenarios, still debated among cosmologists, dark energy's strength could increase over time rather than staying constant. If that happens, the expansion could eventually grow strong enough to overcome every other force in the universe. It would pull apart galaxies, then solar systems, then planets, then atoms themselves, in a hypothetical future event nicknamed the Big Rip. Current evidence doesn't strongly favor this most extreme outcome. But the fate of literally everything in the universe hinges on the detailed behavior of the expansion of space itself. That's only a meaningful question, because space is a dynamic, physical thing, not a fixed backdrop indifferent to what happens within it. There's direct, physical evidence left over from this entire expanding history, faintly filling every direction of the sky, called the cosmic microwave background. About 380,000 years after the Big Bang, the universe had expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. This moment is called recombination. It allowed light to finally travel freely through space, instead of constantly scattering off free-floating charged particles. That first burst of freely traveling light has been stretching, along with the expanding universe itself, for roughly 13.8 billion years since. It has cooled from its original blazing temperature down to a faint microwave glow just 2.7 degrees above absolute zero, arriving at Earth's telescopes uniformly from every single direction in the sky. This afterglow, the cosmic microwave background, was detected by accident in 1965, by radio astronomers Arno Penzias and Robert Wilson. They initially assumed the persistent background noise their antenna kept picking up was caused by pigeon droppings on their equipment, before realizing they had discovered the oldest light in the observable universe. Detailed maps of this background radiation, produced by later missions, reveal extremely tiny temperature variations. The differences are only a few hundred thousandths of a degree, scattered across the sky in a specific pattern. These tiny variations are thought to be the stretched-out remnants of even tinier quantum fluctuations that existed in the earliest fraction of a second of the universe's history. Inflation is thought to have rapidly stretched those fluctuations from microscopic quantum scales up to sizes large enough to eventually seed the formation of every galaxy, every star, and every planet that would ever form. In other words, the pattern of galaxies scattered across the entire observable universe today can be traced back to quantum-scale ripples in space-time itself. They were stretched to cosmic proportions by the expansion of space during inflation. It's a direct, observable link connecting the smallest imaginable scales of quantum physics to the largest imaginable structures in the cosmos, entirely through the medium of expanding, unified space-time. There's a puzzle hiding inside everything discussed so far, one that space-time alone doesn't fully resolve, and it involves why time seems to flow in only one direction at all. The fundamental equations of physics, including Einstein's equations for space-time, are almost entirely symmetric with respect to time. Run the equations, describing a collision between two particles forward, and they describe a plausible physical event. Run the exact same equations backward, and they describe an equally plausible, mathematically valid event. Nothing in the underlying laws forbids it. And yet, everyday experience is filled with processes that clearly only happen in one direction. A cup falls off a table and shatters. Shattered pieces never spontaneously reassemble themselves and leap back onto the table. Cream stirred into coffee spreads out and mixes. It never spontaneously separates itself back into a distinct, unmixed blob. This directional quality of time is called the arrow of time. It doesn't come from the geometry of space-time itself. It comes from a separate physical principle, the second law of thermodynamics. That law states that the total disorder, or entropy, of a closed system tends to increase over time. There are vastly more ways for a system to be disordered than ordered. So, as things evolve randomly, they overwhelmingly tend to drift toward more probable, more disordered states. This means the arrow of time we experience isn't built into the fundamental geometric structure of space-time, the way the light cone structure and causality are. It emerges instead from the extraordinarily low entropy, extraordinarily ordered state the universe happened to begin in, near the Big Bang. The early universe was remarkably uniform and low in entropy. Entropy has been increasing ever since. Every physical process that depends on that increasing entropy, from stars burning fuel to memories forming in a brain, to eggs breaking rather than unbreaking, points in the same direction. That gives us the strong, consistent sense that time flows one way. This is a subtle but important distinction. Space-time's geometric structure, the light cones, the invariant interval, the unification of space and time into one fabric, doesn't by itself explain why time feels like it flows forward. Space, meanwhile, doesn't feel like it flows in any particular direction at all. That extra ingredient, the thermodynamic arrow, tied to the universe's initial low entropy state near the Big Bang, is a separate, additional piece of physics layered on top of the geometric unification of space and time. It connects the abstract four-dimensional structure of space-time back to the very human experience of remembering the past, but not the future. This raises an obvious follow-up question that remains genuinely unresolved. Why was the early universe in such a remarkably low entropy, ordered state in the first place, when the overwhelming majority of possible configurations for a universe would be far more disordered? Physicist Roger Penrose has pointed out that the odds of the universe randomly beginning in a state as smooth and low entropy as the one revealed by the cosmic microwave background are, by his calculations, almost incomprehensibly small. That suggests something specific about the physics of the earliest moments must have set that initial condition, rather than it arising by pure chance. It's possibly related to inflation, and possibly related to an even earlier, still unknown process. This remains one of the deepest unsolved puzzles connecting space-time, thermodynamics, and cosmology together. The geometric unification of space and time has answered an enormous number of questions with stunning precision. But it has also opened up entirely new categories of questions. These are questions that didn't even make sense to ask under the old, separated Newtonian picture, where space was just an empty stage and time simply ticked forward without needing any explanation for why it seemed to only move in one direction at all. There's one more thread worth following, because it points toward the biggest open question left in this entire picture. General relativity describes space-time as smooth, continuous, and perfectly well-defined at every point, no matter how small a region you zoom into. Quantum mechanics is the physics governing atoms and subatomic particles. It describes the universe completely differently, full of probabilities, uncertainty, and quantities that come in discrete, indivisible chunks rather than smooth continuums. These two frameworks, general relativity and quantum mechanics, are each spectacularly successful within their own domains. General relativity correctly describes planets, stars, black holes, and the expansion of the universe. Quantum mechanics correctly describes atoms, particles, and the behavior of light at the smallest scales. But they don't fit together. If you try to apply the smooth, continuous mathematics of general relativity to a region small enough for quantum effects to dominate, the equations stop making sense. They produce nonsensical, infinite answers instead of meaningful predictions. Physicists refer to a specific, incredibly tiny scale called the Planck length, roughly 1.6 times 10 to the negative 35 meters, an almost unimaginably small distance. There's a corresponding Planck time, the time it would take light to cross that Planck length, roughly 5.4 times 10 to the negative 44 seconds. This is the scale at which our current understanding of smooth spacetime is expected to break down entirely. Below that scale, many physicists suspect that spacetime itself may not be smooth and continuous at all. It may have some kind of discrete, granular structure. Think of a photograph that looks perfectly smooth from a distance, but turns out to be made of individual pixels once you zoom in far enough. Nobody has directly observed this granular structure, if it exists. Several competing theoretical frameworks, including string theory and loop quantum gravity, offer different, unconfirmed proposals about what spacetime might actually look like at that fundamental level. What virtually all serious approaches agree on, though, is that the current picture almost certainly isn't the final complete answer. Treating spacetime as a perfectly smooth, continuous, four-dimensional fabric is an extraordinarily accurate approximation. It works beautifully at every scale we've been able to directly test, from laboratory experiments to the orbits of planets to the geometry of the entire observable universe. But it likely breaks down at the extraordinarily tiny Planck scale. It possibly breaks down at the very center of black holes too, and in the earliest instant of the Big Bang itself, where all of that mass, or all of that early universe's density, gets compressed into a space small enough for quantum effects to matter. Finding a theory that successfully merges quantum mechanics with the geometric, unified picture of space-time remains one of the largest unsolved problems in all of physics. It's a search that has occupied some of the most capable minds for the better part of a century, without a confirmed answer yet. One particularly strange symptom of this unresolved tension is known among physicists as the problem of time. Physicists sometimes attempt to write down a quantum mechanical description of the entire universe as a whole, applying quantum rules to the geometry of space-time itself, rather than to particles moving through a fixed background. When they do, they run into an equation called the Wheeler-DeWitt equation. It appears to describe a universe with no time variable in it at all, a single, frozen, unchanging quantum state. This seems to directly contradict everyday experience. We live in a universe that is obviously changing, obviously evolving, obviously experiencing the passage of time in an extremely convincing way. Physicists have proposed several different explanations for this apparent contradiction. One idea is that time might be an emergent property. It isn't fundamental at the deepest level of reality, but arises naturally once you're looking at a large, complex system correlated with other parts of the universe. That's similar to how temperature isn't a property of any single atom, but emerges only when you're looking at the statistical behavior of enormous numbers of atoms together. Under this view, the flowing, one-directional time we all experience wouldn't be a basic ingredient of reality. It would be something closer to an approximation. It's an extremely good, extremely convincing approximation, valid at the scales humans and stars and galaxies operate on. But it's potentially not present at all in the most fundamental, complete description of nature. Nobody has resolved this puzzle definitively. It remains one of the genuinely open, actively debated questions sitting at the boundary between general relativity and quantum mechanics. Even after more than a century of extraordinary success, unifying space and time into a single classical framework, physicists still don't have a complete, final answer for what that unified fabric actually is at the very deepest level nature operates on. Even outside of black holes and the early universe, physicists get to test the unified nature of space and time directly, using machines built right here on Earth. At the Large Hadron Collider, located near Geneva, protons are accelerated to speeds extraordinarily close to the speed of light. They reach within about 11 kilometers per hour of light speed itself before being smashed into each other. At these speeds, time dilation isn't a subtle correction. It's an enormous, dominant effect. Unstable particles created in these collisions would normally fall apart in a tiny fraction of a second if they were sitting still. Instead, they survive dramatically longer as measured by detectors in the laboratory. That's simply because their internal clocks are running so much slower relative to the lab, exactly as relativity predicts. Without accounting for this effect, physicists wouldn't be able to correctly interpret a single collision recorded at the facility. The particles simply wouldn't behave the way the data shows, unless relativistic time dilation was built directly into the calculations from the start. every successful prediction the Large Hadron Collider has confirmed, including the long-awaited discovery of the Higgs boson in 2012, rests on physics that assumes space and time are unified exactly the way Einstein described. They're not separate quantities that happen to interact. They're one combined structure that particles moving near light speed experience completely differently than particles at rest. The unification of space and time also reshapes how physicists think about the future of the universe. It reshapes whether the past, present, and future are as different from one another as they feel. In ordinary experience, the past feels fixed and gone. The present feels like the only truly real moment. The future feels open, undetermined, not yet written. But if you take the four-dimensional space-time picture seriously, all events, at every point in space and every moment in time, exist as fixed points within a single four-dimensional structure. This is sometimes called the block universe. In this view, the past, present, and future aren't fundamentally different categories built into the fabric of reality itself. They're more like different locations within space-time. It's the same way north, south, east, and west are just different directions rather than different kinds of space. Your sense that this current moment is special, that it's the real one, might be similar to how your sense of here feels special. That's simply because it's where you happen to be standing, without here being objectively more real than there. This is a genuinely debated topic among physicists and philosophers, not a settled conclusion. There are serious arguments on multiple sides about how, literally, to take the block universe picture. But the fact that this debate exists at all is telling. Serious physicists take seriously the idea that the future might, in some sense, already exist within the structure of space-time. That's only possible because relativity fused space and time into one geometric object in the first place. Under the old Newtonian picture, this question would never even arise. Time was assumed to be fundamentally different from space, a flow rather than a location. Relativity removed that assumption, and along with it, removed the easy answer. Along the way, it's worth untangling something that often gets blurred together: the difference between the various kinds of redshift discussed throughout tonight. They come from genuinely different physical causes, even though they all involve light stretching to longer wavelengths. Doppler redshift happens when a light source is physically moving away from an observer through space. It's the same stretching effect responsible for a siren's pitch dropping as an ambulance drives away, just applied to light instead of sound. Gravitational redshift happens when light climbs out of a gravitational well, losing energy as it goes. It's the effect measured directly by Pound and Rebka in that basement tower at Harvard. It's the same effect that makes light, escaping from near a black hole's event horizon, stretch toward infinitely long wavelengths. Cosmological redshift is the kind Hubble originally observed in distant galaxies, and it's different from both. It comes from the stretching of space itself, while light travels through it over cosmic timescales. The light's wavelength lengthens, not because the source is moving through space or because it's climbing out of a gravity well, but because the very fabric the light is traveling through has expanded during the journey. All three phenomena stretch light toward longer wavelengths. All three are, at their core, consequences of the same unified space-time geometry. They're just expressed through three different physical mechanisms: motion through space, depth within a gravitational well, and the expansion of space itself. One more consequence of all this is worth carrying with you. because it reaches directly into humanity's long-term future. If our species ever attempts to travel to another star, the Alpha Centauri system includes a small companion star called Proxima Centauri, the single closest star to the Sun. Proxima Centauri sits about 4.24 light-years away. The main pair of stars in the system sits a little farther, at about 4.4 light-years. Even light itself takes over 4 years to make that crossing. For a spacecraft traveling at speeds achievable with current or near-future propulsion, reaching even this nearest neighboring star would take many thousands of years. But if propulsion technology ever advanced enough to push a spacecraft to a significant fraction of the speed of light, something remarkable would happen to the crew aboard it. Time dilation is the same effect measured in muons, GPS satellites, and Scott Kelly's slightly younger body. It would mean the crew experiences the journey passing more quickly, from their own perspective, than someone watching from Earth would calculate. At 90% of the speed of light, a journey that takes about 4.5 years as measured from Earth would feel very different to the crew themselves. It would feel like it took roughly 2 years. Their onboard clocks, their aging, their entire experience timeline would run slower relative to Earth throughout the trip. Push the spacecraft's speed high enough, arbitrarily close to the speed of light, and in principle, a crew could cross vast interstellar, even intergalactic distances within a single human lifetime as they experience it. Meanwhile, thousands or millions of years would pass for everyone left behind on Earth. This isn't a loophole or a trick. It's the same geometric fact about space-time running through everything discussed tonight. Time is not a fixed, universal quantity ticking the same way for everyone. It is a personal measurement of the specific path you take through the combined fabric of space and time. The faster that path moves through space, the less of it gets used up as time, relative to those who stayed behind. Whether humanity ever builds a spacecraft capable of reaching those speeds remains an engineering problem far beyond current technology. But the physics allowing for it is already there. The physics that would let a future space traveler genuinely, measurably, outlive everyone they left behind on Earth without breaking a single law of nature is written directly into the unified structure of space-time that Einstein and Minkowski uncovered over a century ago. Taken together, everything explored tonight traces back to the same single realization. The bending of starlight, the ticking of satellite clocks, the ripples caught by LIGO, the shadow imaged around a black hole, the afterglow left over from the earliest moments of the cosmos. All of it points the same way. Minkowski voiced that realization in 1908. Space alone and time alone are shadows. Only their union has any independent reality. Every experiment designed to test that idea across more than a century of increasingly precise instruments has come back in agreement. Not a single confirmed exception has ever turned up. So why can't space and time exist separately? Because the equations that actually describe the universe only work when space and time are treated as a single combined entity. They've been tested through GPS satellites, particle accelerators, orbiting planets, gravitational waves, and the large-scale structure of the cosmos. Not two independent things bolted together. Try to split them apart. Treat space as absolute and time as a universal, separate flow, and the predictions break immediately. Light wouldn't travel at a constant speed for every observer. GPS satellites would misplace your location by kilometers within minutes. Mercury's orbit wouldn't match what telescopes actually observe. Muons wouldn't reach the ground. The entire structure of cause and effect, of what can influence what, would lose its protection against contradictions. Space and time are not independent stages that reality happens to use. They are two faces of one deeper object, space-time. Which face you happen to see? More space here, more time there. Depends entirely on how you're moving and how much mass is nearby. Mass and energy bend that unified fabric. Velocity reshapes how much of it you experience as space versus time. Near a black hole, the two can trade roles entirely. At the very beginning of the universe, that fabric itself appears to have had an origin rather than existing as an eternal backdrop. None of this is a philosophical add-on to physics. It's the literal mathematical skeleton underneath every confirmed prediction. General relativity and special relativity have made for over a century. The old picture, a fixed stage of space with a universal clock ticking in the background, was comfortable, intuitive, and useful for everyday life. It's also, at a fundamental level, an illusion. Human beings evolved, moving at speeds far too slow, across distances far too small, to notice the seams where space and time are actually joined together. Once you move fast enough, or get close enough to something massive enough, those seams become impossible to ignore. And the universe, when you finally look closely enough, turns out to have never really contained two separate things called space and time in the first place. It contains one thing, wearing two different faces, depending on where you're standing and how fast you're moving. That single, unified fabric is the actual foundation everything else in the cosmos is built upon. Thank you for joining me on this exploration of why space and time cannot exist apart from each other. If you found this journey through relativity valuable, a like or a subscribe helps this channel keep making these deep dives into the cosmos. And the next time you check your phone for directions, or watch the sun set, or simply glance at a clock, remember something. You're not looking at two separate things working side by side. You're looking at a single, four-dimensional fabric, space-time. It's quietly curving, stretching, and flowing beneath everything you do. It ties together every place you've ever been and every moment you've ever lived into one unified structure. Good night. And may you never look at a clock the same way again.